The universe whispers of impossible densities. A neutron star, the collapsed core of a massive sun, pulsates with rhythmic, silent energy across interstellar voids. Its surface, not a liquid or solid in the conventional sense, represents an extreme state of matter where atomic structures crumble under unimaginable pressures. This is a realm where chemistry, as understood on Earth, simply ceases to exist, giving rise to unique physical properties. The immense gravitational pull of a neutron star is the primary architect of its bizarre surface, with a mass exceeding that of the Sun compressed into a sphere merely kilometers across. Gravity here is trillions of times stronger than terrestrial gravity. This crushing force dictates every interaction, warping the very fabric of matter and fundamentally altering its behavior at a subatomic level. At its genesis, a supernova blasts away a star's outer layers, leaving behind a core that collapses under its own immense weight. Electrons are forced into protons, creating neutrons. This process, known as electron capture, fundamentally alters the elemental composition and structure of matter, creating a neutron-rich environment. The neutron star is born from this catastrophic transformation. The surface of a neutron star isn't defined by atomic bonds, but by nuclear forces. Here, normal atoms are ripped apart. Electrons, no longer bound to nuclei, form a degenerate electron gas, creating a metallic-like crust. This outer layer, though incredibly dense, still retains some semblance of ordered nuclei, existing in conditions beyond earthly comprehension. Deeper within this crust, the pressure intensifies. Atomic nuclei become increasingly neutron-rich, packing together tighter than anything observed in terrestrial laboratories. This exotic material, sometimes referred to as nuclear pasta, forms complex, interwoven structures under the overwhelming gravitational squeeze, resembling cosmic spaghetti or lasagna filaments. Chemical bonds, which rely on electron sharing or transfer between atoms, are utterly irrelevant in this extreme environment. The electrons are no longer localized to specific atoms. Instead, they are a vast sea of particles contributing to the overall degenerate pressure that prevents further gravitational collapse. This negates the very foundation upon which chemistry is built. The strong nuclear force, which binds protons and neutrons together, becomes the dominant interaction, overriding the electromagnetic force that governs chemical reactions. Elements as we know them do not exist in their familiar forms. Instead, matter forms a fluid-like state of free neutrons, protons, and electrons, tightly packed and governed by quantum mechanics at its most extreme. The entire structure of a neutron star, from its crust to its core, is a manifestation of extreme physical laws. Instead of a chemically diverse planet, it is a gradient of nuclear densities. The outer crust, sometimes referred to as the outer ocean, contains nuclei with a diminishing number of electrons, existing in a lattice structure sustained by the intense gravitational field. Beneath this outer ocean lies the inner crust, where the density reaches staggering levels. Here, the nuclei begin to merge, and unbound neutrons start to drip out of them, forming a superfluid. This superfluid of neutrons coexists with the remaining heavy nuclei, creating a state of matter utterly alien to terrestrial experience, where particles can flow without resistance. The core of a neutron star is the ultimate realm of uncertainty for astrophysics. Theoretical models suggest a soup of exotic particles, hyperons, quarks, and gluons, existing in a plasma state. This extreme density could even lead to a quark-gluon plasma, a state where the fundamental building blocks of protons and neutrons are no longer confined within them. The incredible magnetic fields of neutron stars, often trillions of times stronger than Earth's, further influence the surface phenomena. These fields are so intense they can quantize the motion of electrons, forcing them into specific orbits around magnetic field lines, even in the absence of traditional atomic nuclei. This fundamentally alters their behavior. The extreme temperatures, often millions of degrees Kelvin, also contribute to the breakdown of conventional chemistry. While cooling over cosmic timescales, the initial temperatures are so high that any complex molecular structure would be instantly vaporized. The energy levels involved far exceed the binding energies of chemical bonds. Unlike a planet where geological processes shape its surface through chemical reactions and erosion, the surface of a neutron star is governed by nuclear physics and relativistic effects. Its topography, if it can be called that, is formed by the interplay of immense gravity, intense magnetic fields, and the degenerate pressures of its constituent particles, rather than chemical weathering. Therefore, the laws of chemistry, which fundamentally describe the interaction of electron shells around atomic nuclei to form molecules, are simply inapplicable. On a neutron star, the forces at play are the strong nuclear force, gravity, and electromagnetism at a scale that overrides electron-based interactions, rendering conventional chemistry obsolete. To truly grasp the neutron star's surface, one must discard terrestrial analogies. Earthly surfaces are shaped by atmospheric interaction, liquid erosion, and complex mineralogy, all products of chemical bonding. A neutron star's surface experiences none of these. Its atmosphere is a thin layer of electron-positron plasma, and its geology is nuclear. Consider the common rock on Earth, a lattice of silicon and oxygen atoms held by electromagnetic bonds. Even the strongest materials, like diamond, derive their rigidity from electron sharing. On a neutron star, these bonds are overwhelmed. The density is such that a sugar cube of neutron star material would outweigh all terrestrial mountains combined, a stark comparison to everyday matter. The very concept of a molecule implies discrete atoms held together by electron interactions. This is foundational to chemistry. On a neutron star, the constituent particles, primarily neutrons, are so densely packed that they interact directly via the strong nuclear force. There are no individual atoms in the traditional sense, thus no molecules or compounds. Even the concept of phase is redefined. On Earth, water transitions from solid to liquid to gas through changes in molecular kinetic energy. On a neutron star, phases relate to the organization of nuclear matter, the solid-like crust, the superfluid neutron interior, and potentially the quark-gluon plasma in the core. These are nuclear, not chemical, phase transitions. The exotic phenomena observed on neutron star surfaces, such as starquakes or rapid cooling, stem from nuclear processes, not chemical ones. A starquake, for instance, is thought to be caused by cracks forming in the incredibly rigid, crystallized crust of neutron-rich nuclei, releasing immense amounts of energy. This is a cosmic tectonic event driven by nuclear material stresses. Terrestrial experiments, even those mimicking extreme pressures, cannot replicate the neutron star environment. While scientists can create incredibly dense materials or superhot plasmas, none can sustain the combination of gravitational pressure, magnetic field strength, and neutron degeneracy that dictates the chemistry of a neutron star. Its state is unique to the cosmos. The very definition of an element, based on the number of protons in an atomic nucleus, blurs on a neutron star. While some heavy nuclei might persist in the outer crust, they are so severely deformed and neutron-rich that their properties diverge wildly from their counterparts on the periodic table, illustrating a breakdown of fundamental chemical classification. Even cosmic entities as stable as neutron stars are subject to the relentless march of thermodynamic laws. Over eons, these ultra-dense remnants undergo a slow, inexorable process of cooling, a cosmic failure to maintain their initial thermal energy. This cooling profoundly impacts their observable properties and internal dynamics. Immediately after their formation in a supernova, neutron stars are incredibly hot, often reaching trillions of degrees Kelvin in their core. They rapidly cool through the emission of neutrinos, weakly interacting particles that escape the star almost unimpeded, carrying away vast amounts of thermal energy. This initial phase is swift and efficient. As the neutron star ages, typically after a few thousand years, the neutrino emission mechanisms become less dominant. The cooling process transitions to slower radiative cooling, primarily through the emission of X-rays from its incredibly hot, but now significantly cooler, surface. This gradual energy loss marks its slow descent towards thermal equilibrium with space. In binary systems, neutron stars can interact with companion stars, often drawing in matter. This process, known as accretion, transfers mass and angular momentum to the neutron star, causing it to spin faster and potentially accumulate more material. This dynamic interaction leads to significant changes in the neutron star's fundamental properties. The accretion of matter onto a neutron star's surface can trigger thermonuclear bursts, known as X-ray bursts. The incoming hydrogen and helium from the companion star ignite explosively under the extreme gravity and temperature, releasing colossal amounts of energy. This is a temporary but dramatic departure from the star's quiescent state. However, a neutron star has a theoretical maximum mass, known as the Tolman-Oppenheimer-Volkoff (TOV) limit, beyond which the degenerate neutron pressure can no longer support its own gravity. This limit is estimated to be around 2 to 3 solar masses, representing a critical threshold for its stability and existence. If a neutron star accretes enough mass to exceed the TOV limit, its structure collapses. The neutron degeneracy pressure, the very force that prevents it from shrinking further, is overcome. The star undergoes a final irreversible collapse, transforming into an even more compact and enigmatic object, a stellar mass black hole. The collapse into a black hole is an event horizon, a point of no return where space-time itself becomes infinitely curved. No information, not even light, can escape this region. The very existence of the neutron star, a beacon of ultra-dense matter, is erased from the observable universe, replaced by a gravitational singularity. This final act is not a chemical reaction, but a fundamental transition in the state of space-time and matter. The forces that once held the neutron star together, primarily the neutron degeneracy pressure, are simply overwhelmed. The object crosses the threshold where gravity reigns supreme and absolute, defining its ultimate fate. The energy released during such a hyperaccretion event and subsequent collapse can be immense, potentially driving phenomena like gamma-ray bursts, some of the most powerful explosions in the cosmos. These bursts are the final fleeting signals of a neutron star's demise, often outshining entire galaxies for a brief period. Furthermore, neutron stars can lose angular momentum over time. Pulsars, which are rapidly rotating neutron stars, gradually slow their spin due to the emission of electromagnetic radiation. This spin-down, though slow, is an energy loss mechanism, contributing to the star's overall thermodynamic degradation over astronomical timescales. In rarer cases, two neutron stars in a binary system can spiral inward and merge. This cataclysmic event, observed through gravitational waves, creates an even more extreme environment. The merger often produces heavier elements through rapid neutron capture. Our process nucleosynthesis and can either form a supermassive neutron star or a black hole. The aftermath of such a merger is a chaotic maelstrom of matter and energy. The combined mass can briefly form an unstable hypermassive neutron star that quickly collapses or directly create a black hole. This gravitational wave-emitting finale marks a profound restructuring of the local spacetime and a violent end to the original stars. Thus, the failure of a neutron star is not a decay in the chemical sense, but a thermodynamic and gravitational breakdown. It is either a slow cooling into cosmic oblivion, a violent explosion fueled by external accretion, or a final, irreversible collapse into a black hole, dictated by the immutable laws of extreme physics. The existence of a neutron star stands as a stark reminder of the universe's capacity for extremes. It is a cosmic artifact where the familiar laws governing matter and energy are bent, broken, and rewritten. Its silent, dense presence across the void challenges our intuitive understanding of the physical world. From the intricate dance of electrons in a chemical bond to the crushing weight of a neutron star's gravity, the universe unfolds its principles on scales unimaginable. A neutron star's surface, a nuclear realm rather than a chemical one, embodies this profound difference, operating under a rule set entirely alien to our terrestrial experience. Humanity's journey to comprehend these celestial objects is a testament to the power of scientific inquiry. Each observation, each theoretical model, peels back another layer of the cosmos's complexity, revealing a universe far more intricate and dynamic than once conceived, driven by forces we are only beginning to fully grasp. The sheer density and gravity of a neutron star force us to confront the limitations of our everyday perceptions. It teaches that the laws we observe are often context-dependent, applicable to certain regimes of energy and matter, but fundamentally altered when pushed to the ultimate boundaries of physical possibility. In the vast, silent arena of space, objects like neutron stars stand as monuments to physics, not chemistry. They are a constant reminder that the universe, in its most extreme manifestations, operates on principles that defy our common understanding, urging us to question and explore what other fundamental laws of nature might be completely different on the surfaces of other exotic cosmic bodies.